Okay, in this video we'll talk about absolute maxima and minima of functions. So, absolute maxima and minima. So this is usually explained in calculus. Basically what happens is once you learn the definition of a derivative and then learn some properties like the product rule and the quotient rule and the chain rule and implicit differentiation, then there's usually a chapter on applying derivatives to understanding graphs of functions and how functions behave. And one of the applications is to find absolute maxima and minima. But the concept of an absolute maximum and minimum really has nothing to do with derivatives. I mean, you can use derivatives to figure out where they are, but in terms of what it is, it's not about derivatives or anything. So the idea is that if you have some function, okay, something like that, then the absolute maximum value of function is the biggest y value that's achieved by the function. So in this case, it would be this y value. Let's call this y value, y0. So then we would say that y0 is the absolute maximum of the function. So let's call this y equals f of x. Let's assume that the graph just goes down forever, so like that. y0 is the absolute maximum of f of x, and it's attained at, so let's say this point has x value x0, attained at x equals x0. So that's the idea. Now let's go to the definition. So the function f, and now here I'm assuming that f is defined only on an interval, has an absolute maximum value on an interval if there is some number c in the interval such that f of c is greater than or equal to f of x for all x in the interval. In this case, f of c is called the absolute maximum value of f on the interval. So let's look at some examples. Let's just look at a straight line. Let's look at y equals 2x. And let's look at the closed interval from 1 to 4. Okay, so when x is 1, y is equal to 2. When x is 4, y is equal to 8. So it goes through these 2 points. And goes through the origin. Okay, not the best picture. It should be a straight line, but whatever. Okay, so on the interval from 1 to 4, this closed interval, the y values go from 2 to 8, right? So, and notice that the value of 8, that's the biggest value, it's actually achieved by plugging in 4. So f of x equals 2x has an absolute maximum value of 8. Now notice that the absolute maximum value is the value of the function. Okay, it's a value of y, not a value of x. So it has an absolute maximum value of 8 at x equals 4. That's what we would say. On the interval, the closed interval from 1 to 4. Okay, so this is a correct statement. And actually, there's a concept of absolute minimum value, as you might expect. So instead of rewriting the definition all out, I'll just say that if you wanted the absolute minimum value, that's when f of c is less than or equal to f of x for all x. So an absolute minimum value on an interval is attained at a number c if the y value at c is less than or equal to all the other y values in the interval. So for instance, in this example, you also have that f of x equals 2x has an absolute minimum value of what on the interval 1, 4? 2, right, at x equals 1. That's the smallest y value on the interval 1, 4. Now the y values get smaller and smaller when x is less than 1, but here we're only looking at the closed interval from 1 to 4. Now let's see what happens if you change the closed interval to an open interval. So it's the same function, okay? It's better to draw the line first, isn't it? And then label the points. So let's look at this function, but only on the interval, the open interval from 1 to 4. So remember, the open interval means you don't include 1 and you don't include 4, but you include everything between 1 and 4. Well, in this case, there is no absolute maximum value. There is, one way to put it is, there's no absolute maximum value of the function f on the interval 1 to 4. How come? Because the value 8 is not attained, right? 4 is not in the domain of the open interval from 1 to 4 because we excluded 4 from it. So if you look at what's going on with the y values, as x gets closer and closer to 4, what's happening? Okay, the y values attain all the values from they attain all the values from, say, 6 when you plug in x equals 3, from 6 up, except you exclude 8. And similarly, the function, there is no absolute minimum value of f on the interval from 1 to 4. Again, because all the values of the function are bigger than 2 and they're never equal to 2. Okay, so when we exclude the endpoint, sometimes there are problems. Let's look at another example. Let's look at f of x equals negative x squared on the half open interval from negative 3 to 2. So this means that we exclude negative 3, but we include 2. Okay, let's see what happens. So let's look at the graph of the function. So here's negative x squared, right? And when you plug in negative 3, you get negative 9. Why don't we just try to make this a little more accurate, more to scale. Okay. You get negative 9. Now notice that negative 9 is not attained by the function negative x squared because you're not including negative 3 in the domain. And when you plug in 2, you get negative 4. So this point here is negative 3, negative 9. This point is 2, negative 4. So here's negative 4. Okay, but this is included. So the graph of the function is this. You have an open hole here, and then it's this piece of the parabola, and you include this point. Now let's look at the absolute maximum. Well, notice that actually the absolute maximum is achieved. The function has an absolute maximum value of, so what's the biggest y value? It's actually 0. Right? If you look at how high this parabola goes, the highest is this point here. This is 0, 0. The biggest y value is 0, 0, and this is achieved at x equals 0. What about absolute minimum? Is there a smallest y value? Well, no, because when you look at the y values, they get closer and closer to negative 9, but they never reach negative 9. The function does not have an absolute minimum value on the half of an interval from negative 3 to 2. Okay. Let's look at some more examples to see what things can happen. So let's say I had this function f of x equals x over 1 minus x squared. Well, this function looks like let's just look at it from negative 1 to 1. There's a vertical asymptote. It looks like this. Now this function, does it have an absolute maximum or minimum? No, because the y values surpass every possible y value, right? There's no biggest y value because these y values, as x gets closer and closer to 1 from the left, these y values are going off to infinity. They're just getting arbitrarily large. And similarly, there's no absolute minimum value because as x goes to negative 1 from the right, the y values just get more and more negative, and they get arbitrarily negative, right? It's not like they somehow stabilize to like negative 100. That's the biggest it can get. It just gets more and more negative forever. So the values get arbitrarily small. Okay, so we would say that this has no absolute maximum value and no absolute minimum value. Well, we're only looking at the interval from -1 to 1, but and this function has values, outside. I mean, you can plug in values bigger than 1 and less than -1 and see what you get. But if you think about it, we already know that there's no absolute max or absolute min anywhere, because we know that the y values just in this interval from -1 to 1 are going to surpass any possible y value, and they're going to surpass, in the negative direction, any negative y value. Let's see. I think we have like 3 more examples. And by the way, negative infinity to infinity does count as an interval. Okay, so let's say that you had this piecewise function x plus 1 if x is less than 1, and x squared minus 6x plus 7 if x is greater than or equal to 1. And so this is a piecewise function. Let's look at the graph. X equals 1, the y value is 2. Just goes down like this. And then when x is equal to 1, you plug it into the quadratic function, you get 1 minus 6 plus 7 is 2. This actually gets filled in, and it's this parabola. Right, so that's what this function looks like. And let's look at it from -5 to 4. -5 to 4. Well, when you plug in -5, you get this point, -5, -4. And when you plug in 4, you get 4, -1. And this point's 1, 2. So let's look at this function on the interval -5 to 4, the closed interval. Does this have an absolute max or min? Let's think about the absolute maximum value. Is there a biggest y value when x ranges from -5 to 4? Well, it looks like it, right? It's this point here. So the absolute maximum of f on the closed interval from -5 to 4 occurs at x equals 1, and the absolute maximum value is f of 1, which is 2. What about the smallest? Is there a smallest y value on this closed interval? Yes, there is. It's here. This is the most negative value. Here we're just looking at the graph, right? I mean, this is the most negative it gets, and it's actually achieved. The absolute minimum value of f, the absolute minimum of f, okay, and we should say the absolute minimum value of f on the closed interval from -5 to 4 occurs at -5 and is equal to f of -5, which is -4. So the absolute maximum value of f is 2, and the absolute minimum value is -4. Okay, one more example, and then we'll take a look at this absolute max and mins on the whole real number line. So let's look at another example of a function with the asymptote. Well, this is, we basically already did this example before, so you have a vertical asymptote at x equals 3, and it looks like this, right? It's just 1 over x shifted by 3 to the right. So it looks like this, and let's say that you have the interval from 1 to 5, the closed interval from 1 to 5. Well, this function does it have an absolute max or min on the interval from -1 to 5? No, because you have this vertical asymptote, and when x is a bit bigger than 3, so as x approaches 3 from the right, the y values, I mean, they just go off to infinity, so they attain every possible y value, and that's positive. And then as x goes to 3 from the left, the y values get arbitrarily negative. So there's no biggest y value and there's no smallest y value that's achieved. So this has neither an absolute maximum value nor an absolute minimum value on the closed interval from 1 to 5. Okay, I hope that gives you a good idea of what absolute maxima and minima are. Now, so in the previous definition, in the definition I've given, it's just absolute max and minimum values on an interval. But we can actually talk about, the same concept applies where you just look at all values of x in the domain. So definition, f of c is said to be, so c is an element, c is a value in the domain of the function. It's said to be an absolute maximum value of the function f if c is in the domain of f and f of c is less than or, sorry, greater than or equal to f of x for all values of x in the domain of f. And there's a similar notion of absolute minimum value. It's just when f of c is less than or equal to f of x for all x in the domain of f. Let's look at some examples. Let's actually look at, I didn't do this example previously, but maybe I could have. Let's just look at a constant function. Okay, let's just look at f of x equals 3. Does this have an absolute maximum value? Well, intuitively, you might say no, right? You might say, well, there's no value that's bigger than all the others. But look at the definition that we're using. A number is an absolute maximum value if, okay, f of c is greater than or equal to f of x. So it doesn't have to be bigger than all the other y values. It just has to be bigger than or equal to all the other y values. And 3 is, in fact, bigger than or equal to all the other y values because it's equal to all the y values. So this function, f of x equals 3, has an absolute maximum value of 3. And it's attained at every real number, x. And let's think about the absolute minimum value. That's a value, that's a y value that's less than or equal to all the other y values. So if you think about it from the definition, then yes, f of x equals 3 also has an absolute minimum value of 3, also obviously attained at every x value, at every real number x. So this might, not be very intuitive because you're used to thinking of, the maximum as like the biggest. But if you think about all the y values, right, 3 is the biggest, so it kind of makes sense. I mean, let's say a bunch of people took a test and, everyone got 90. Well, then the biggest score was 90, right? And the smallest score was also 90. So it kind of makes sense. I mean, you wouldn't say, well, there was no biggest score. I mean, there is a biggest score. It's 90. And it's the same concept with this function. All the y values are 3, so you would say that the biggest y value is 3 and the smallest y value is also 3. Okay. So let's look at an example. Let's look at this parabola f of x equals x squared minus 4x plus 8. So we know that this is an upward pointing parabola, and the vertex turns out to be 2, 4. You can use the formula negative b over 2a, right, to get x, and you plug in to get the y value, so you get this. Okay, so when we say, just to emphasize, the absolute maximum or minimum value of the function, we're talking about, right, without referring to an interval, we're talking about when you look at all the x's in the domain, all the possible y values that you get. So this does have an absolute minimum value, right? This function has an absolute minimum value of what? Of 4 at x equals 2. Because this y value is achieved when you plug in x equals 2, and it's smaller than or equal to all the other y values of the function, because all the other y values are, well, in this case, they're all bigger than 4. But does this function have an absolute maximum? No, because as x goes out to infinity or to minus infinity, all the y values are achieved. So there is no absolute maximum value of f. Okay, that's absolute maxima. That's absolute maxima and minima. And I could go on and talk about local maxima and minima, but I think I'll just leave that for a different video. Okay, thanks.